Hello dear students, welcome back to the lecture series on theory of semigroups with course code MMTE 405. Today in this lecture we are going to discuss semillatice. So for this we define partially ordered set. Given a non-empty set and a relation on that set X, omega is a relation on that set X, that means omega is the subset of X cross X, then this omega is called partial order, or simply we can say it's called a order if it has the following properties. First property, this omega should be reflexive. So reflexive means x comma x belongs to omega for all x belongs to x. And second property, it should be symmetric. It should be antisymmetric. Antisymmetric means for all x comma y belongs to x, for all x comma y belongs to x, with the xy belongs to omega and yx belongs to omega, then this should imply x equal to y. Implies x equal to y. So this is called antisymmetric. Antisymmetric. And third property is it should be transitive. Transitive means for all x, y, z belongs to x, with x comma y belongs to omega and y comma z belongs to omega. This implies x comma z belongs to omega. So any relation on X is called partial order. If it's reflexive, this one it's called reflexive here. This property is called reflexive. Second, it should be antisymmetric. Antisymmetric means whenever xy is in omega and yx is in omega, then x should be equal to y. And third one, it should be transitive. Transitive means whenever xy is in omega, yz is in omega, xz should be in omega. So any relation having these three properties is called an order on X. And this omega is usually denoted by we write x less or equal to y. We write x less or equal to y rather than this xi belongs to omega. So whenever xi belongs to omega, we write x less or equal to y. So this partial order relation is usually denoted by that notation, less or equal to notation. Okay. So if say x is less than y, y is less than x, okay, then it means that x is greater than y, x less than y, x greater than y, and you can say this x greater or equal to y. This denote that x is not equal to y, with x comma y belongs to omega. And second means x is not equal to y, with x not x comma y, y comma x is in omega. And third means either x equal to y or y comma z, y comma x, it is just y comma x belongs to omega. So whenever we write x is strictly less than y, it means that x is not equal to y, and x and y they belong to omega, they are in the relation, they are in this omega. And whenever x is greater than y, it means that y comma x is in omega and x is not equal to y. And when x is greater or equal to y, this means that y comma x is in omega. Y may be equal to x in this case. Okay. Next, we define the upper bound. So if x with this relation is a partial, you do not put this is a partial. So x with the relation less or equal to, which is order, is called partially ordered set. If x less or equal to this order here is a partially ordered set, is a partially ordered set. So partially ordered set means the set X together with partial ordering on that set X. Less or equal to is a partially ordered relation on that X. Partially ordered means it's reflexive, it's antisymmetric, and it's transitive. So suppose this set is partially ordered set, and Y is a subset of X. Y is any subset of X. Then we say an element C of Y, then an element C of X is called a lower bound. It's called a lower bound if C is less or equal to Y. Is called a lower bound of Y, that subset, that particular subset Y of X. If C is less or equal to Y for all Y belongs to Y. For all Y belongs to Y. Then we define the least greatest lower bound. So it's the maximum of all the lower bounds actually. The maximum of all lower bounds of a given set. So how we define greatest lower bound? If the set of lower bounds, if the set of lower bounds of Y is non-empty, So suppose Y is a given subset of X, then we have defined this. We have defined this the lower bound of a set Y. It's an element C such that C less or equal to Y for all Y belongs to Y. So if this set of lower bounds of a given set Y is non-empty, then we choose the maximum element of this set and has a maximum element So it is a set of the lower bounds, and this set of lower bounds has maximum element. Maximum element, say D. Let us denote that maximum element by D. We say that D is the greatest lower bound of Y, or meet of Y. We say that D is the greatest lower. We say that D is the greatest lower bound. D is the greatest lower bound. D is the greatest lower bound. Greatest lower bound. Greatest lower bound, or you can say meet of Y. Meet of Y, and it can be written as and we write it as D is equal to, it's this Y, where Y belongs to Y. So this notation, this is the notation for the greatest lower bound of the set Y, and it's also called the meet. Okay. Now in case this Y is consisting of only two elements, suppose Y is equal to A comma B. So this is the general definition for any subset of Y of X, but in case this Y consisting of only two elements, then we write this greatest lower bound is equal to A meet B. That notation for two elements subset. Okay. Now if X less or equal to is a partially ordered set, such that for all A comma B belongs to X, A meet B exists. Means the greatest lower bound of any two element subset exists, any two element subset Y of X exists, then we say that partially ordered set is a lower semillatice. Then x less or equal to is called a lower similatice. It's called a lower similatice. Okay. In case for any subset y of x, the greatest lower bound of any subset y of x exists, in that case we call x less or equal to complete lower simulates. Okay. So if it exists for any subset of x, we call it complete lower simulates. If for any subset y of x, the element meet of y belongs to y exists, then this partial ordered set x with this relation less or equal to is called a complete lower similatice. So complete means the lower bound, the greatest lower bound exists for any subset y of x, and lower similatice means that the greatest lower bound of any two elements a comma b of x exist. Okay. So in other words, we can say that every complete lower similatice is a lower similatice, because for complete lower similatice, any subset y of x, its greatest lower bound always exists. So in particular, for any two element subset y of x, the greatest lower bound of that subset exists. So hence it's a lower similatice. So every complete lower similatice is a lower similatice. Okay. So on similar lines, we define the join y belongs to y, the least upper bound for any subset y of x, or the least upper bound. We define on similar line, we define this, and we define the least upper bound of any two element subset of x. And we can on similar lines we can define this, and then we define we give an analog definition of this complete upper similatice, and we define complete upper similatice. So complete upper similatice means if the least upper bound of any subset y of x exists, then this partially ordered set x is called a complete upper similatice. And we can define the upper similatice, complete upper similatice and upper similatice. So upper similatice means that for any two elements a and b of x, their join exists. The least upper bound always exists in that space. So this is the definition of complete upper similatice. It's the analog of that definition of this complete lower similatice and lower similatice. Just instead of meet, we are taking here join. Their join should exist. So in case if the partially ordered set x with relation less or equal to x is if it is both if it is lower similatice as well as upper similatice, or you can say complete lower similatice, lower, and upper similatice, or you can or complete upper similatice, complete upper semillatice. If the partially ordered set X, if this is both lower semillatice and upper semillatice, or both complete lower semillatice and complete upper semillatice, then this partially ordered set X is called semillatice, is called semillatice. And in case it's both complete upper semillatice and complete lower semillatice, in that case it's called a lattice. So lattice means which is both complete upper semillatice and complete lower semillatice, that's called a lattice. Now one can easily verify that if X with relation SR equal to is a lower semillatice, is a lower semillatice, one can easily verify that if this X with this relation SR equal to is a lower semillatice or upper semillatice, then for all ABC belongs to X, this meet of three elements ABC is equal to A meet B meet C. And in case of upper semillatice, page number 4, in case of upper semillatice, you can say in brackets it's A join B join C is equal to A join B join C. So if X is lower semillatice, then for all A, B, C in X, A meet B meet C is equal to A meet B meet C. This can be easily verified because A meet B meet C, it's actually the greatest lower bound of three elements A, B, C. And A meet B meet C, it's again the greatest lower bound of three elements A, B, C. Therefore both are equal because greatest lower bound is always unique if it exists. And here it exists because we are in lower semillatice. And similarly for upper semillatice, this holds. This is true. Huh? So now we have a following theorem. So therefore we can say first we write this. Therefore this is therefore this X together with this operation, if X is a lower semillatice, then therefore if X is a lower semillatice, so I will define only one lower semillatice, the second follows on similar lines. So therefore if this is a lower semillatice, then this together with this binary operation, because for any A, B in X, A meet B exists, it's always in X, then this is a semigroup, you can easily verify it because it satisfies the associative property also for lower semillatice. If we take this as a binary operation, meet operation as a binary operation, then it satisfies this associative property. And also it's a binary operation because for all for all A comma B belongs to X, A meet B, it also belongs to X, it exists because it's a lower semillatice, and it satisfies this property also, associative property. So that means this is a semigroup if it is a lower semillatice. Now next we have a following theorem which gives the connection between the lower semillatice and a commutative semigroups with each of element is idempotent. That's next theorem. So let E together with this relation less or equal to is be a lower semillatice. Suppose it's a lower semillatice. Be a lower semillatice. Then E together with this operation is a commutative semigroup. Is a commutative semigroup consisting entirely of idempotents, means each of element of E is idempotent. Is a commutative semigroup with each element of E is idempotent. With each element of E is idempotent. So if it's a lower semillatice, then E together with this operation meet. It's a commutative semigroup with each element of E is idempotent. And not only this, and for all A comma B belongs to E, A less or equal to B if and only if meet of A and B is equal to A. If and only if meet of A and B is equal to A. And conversely, suppose that conversely also true. Conversely, suppose that E with operation say dot denote multiplicative operation, if it is a commutative semigroup, is a commutative semigroup with each element of E is idempotent. With each element of E is idempotent. With each element of E is idempotent. Then we can define a relation on E such that relation makes E lower semillatice. Then we can define such relation. Then the relation. It's just a semigroup, commutative semigroup with each element of E is idempotent. There is no relation on E. So now we can define the relation. We can define a relation on E. So define the relation less or equal to on E, but